Hello and welcome to this short tutorial for the steel flat plate X bracing design spreadsheet to Eurocode 3 and the UK National Annex. So to get this spreadsheet, you're going to need to go to my website and click on this icon here. It's going to download a zip folder with a PDF worked example inside it and a spreadsheet which allows you to design this flat plate. In this tutorial, we're just going to be focusing on the spreadsheet itself. So if I go down here, I'm going to go to the spreadsheet. I've already got it open. I'm going to skip over a bunch of the project info and a bunch of the database options in here for saving and loading the design, because they're the same as all of the other spreadsheets on my website, and I've covered them in detail elsewhere. And this is quite a simple basic spreadsheet, so I don't want to go into massive amounts of detail about how to save and load your design from the design sheet into these saved designs and how to deal with this project info. I'm just going to focus on the design of the flat plate bracing itself. So this design sheet is basically set up when you're looking at designing a set of cross bracing inside a building. So for example, if I look at a steel frame, this is my sort of drawing of a steel frame on elevation. We may have a braced bay within the steel frame, so we'll have some X bracing in here, and typically this is used to basically support any kind of lateral forces we'll have on the building. So if we've got any lateral forces in here, we'll end up with tension in one of these members in here. Well, that's actually going to cascade through the structure, but essentially we're going to end up with some of these elements in tension, and we want to design those to make sure that the member itself is okay in tension, so the actual flat plate piece of steel is okay, so like the rectangular chunk of steel is okay when we've got a tensile force applied to it, but also locally around the bolted positions as well, to make sure that we're happy with that. So that's what the spreadsheet allows us to design, and within the spreadsheet itself we've got all these numbered sections here that we can fill out in order, and all of the light yellow cells are input data, and all of the other cells are basically cells that you shouldn't be messing with. They auto calculate all their headers. So if I go to the spreadsheet here and go into section 1, we can define the geometry of the flat plate. So it's a rectangular bit of steel that we're looking at, so we can define the thickness of the flat plate and the width of the flat plate. So for example, if I go back to my drawing here, the width would be this dimension, and our thickness would be, if I draw it like that, our thickness would be this dimension in here. If I go back to the Excel, you can see that there's a diagram here which shows you where those dimensions are as well, so you can use that for reference. Those are defined in millimeters. Next we have our material properties, so we can define our grade of steel. We can have S275, S235 or S355. The program will automatically calculate our ultimate tensile stress if we put in auto in this box. We can also set it to manual and then define a manual value in here. So if I put in 450 for example, it will set my ultimate tensile strength as being 450. If we went back to auto, it would also set that based on the tables within the Eurocode. Okay, so that allows us to set our material properties. Section 3 allows us to define our bolts, so our bolts that go through this bit of flat metal to bolt it onto the rest of the structure. Typically speaking, at our connection point, if I just draw this quickly, we'd have a flat bit of metal like that, which is our brace, and then at the support we've got like a column for example like that, and maybe a beam at the top here. We'd probably have some sort of gusseted plate in here, and then we'd be bolting through onto that for example. This design sheet is only looking at the actual flat plate itself, so it's only looking at this bit of the metal in here. If you were to design the full building, you'd want to actually make sure you check this gusseted plate as well as any kind of welds that we have along these surfaces here where we're connecting it back to the main structure. Okay, so that's basically what we're dealing with here. Let's just clear that. Back to the bolts. So we can define the size of our bolts here, so we can define M12s up to M30s. We can define the bolt class, so the strength class of the bolts, with a 4.6 to 10.9. We can and it will automatically set that as a hexagonal head bolts in here. This spreadsheet doesn't deal with countersunk bolts. If you're defining countersunk bolts, you can't use the spreadsheet because the countersunk bolts will give you a reduced capacity of the section, and the reason for that is if I draw a section through with a countersunk bolt, so this is sort of looking end on of our flat bit of steel, the countersunk bolt will have a kind of notch into the actual steel plate in here, like that, So we're going to have a reduced area when we're looking at this bit of steel over here, for example. And we'll have also localized bearing pressures along these kind of edges and stuff when we're looking at that. So countersunk bolts are not dealt with in this spreadsheet. We can only look at, you know, a hexagonal head bolt where we have a straight hole through the section. So a hexagonal head bolt like that, where we have a straight hole through the section in this area in here. Okay. Back to our spreadsheet. So we can define also as well underneath here whether we're loading the section up in single shear or double shear, and there's a little button here you can click which will give a diagram showing you what I mean by that. It's basically to do with the number of shear planes that we're looking at for the bolt. So here we've just got a single bit of steel connected to like a thin plate type of connection, so that would be a single shear because there's a single plane of shear through the bolt, whereas in this situation where we've got sort of two bits of steel with our brace sort of sandwiched in between, we've got two shear planes through the bolt. And clearly the double shear situation is going to give us a much more beneficial situation with our bolts than the single shear, because we're basically applying our load over twice as much area as we would be with the single shear. So when in doubt, when you don't know what's going on, pick the single shear, as that's going to give you the more conservative result. Back to our design, we can define the number of our bolt rows and the number of our bolt columns. So at the moment I've got a single row of bolts and two columns, and if we go down here to section 7 we can see that plotted. We can see our rows of bolts and everything, and if I type in 2 in here for example, or select 2, we can see we've now got 2 rows of bolts. And again, if I go up to this diagram here in section 6, we can see that as well, how that's being applied, how our rows and everything are being defined. If I go back down here, so now I've defined 2 rows and 2 columns for our bolts. We can define the spacing between our bolt rows and our spacing between our bolt columns in millimeters. And then we can also set our bolt hole clearance diameter. So basically this is the actual diameter through the steel when we have a bolt. So if I talk back to the drawing again, if I have my steel end on like this, and I have a bolt which is going through the steel, then our clear distance is the actual distance in here, this distance there. Because if I had like an M10 bolt, if this was an M10, clearly I need a larger distance. I need this D here needs to be bigger than 10 millimeters in order to allow us to actually get the bolt through here, because I need some clearance. This bolt here, if that's 10 millimeters for my bolt, I need some clearance in this space here in order to get that bolt through. So that allows us to define that bolt clearance diameter in here. So we can set that as being auto, and it will give us the auto distance, which is 17.5 here for our M16s, or I can set it to manual and put a manual value in here if I want to. So let's put 17 in there. That's going to set that for me. And then down the bottom here we have the auto-calculated minimum edge distances for the bolt columns and the bolt rows. And these are worked out based on the bolt diameter. And we can look over here on our diagram and it will tell us as well our minimum edge distance, which here is calculated as 1.25D, and our bolt spacing is set as a minimum as 2.5D, which is sort of standard bolt spacings. Okay. Once we've set all of that, we can define our applied loading at ultimate limit state at ULS in section 4, and in this case I've set my maximum axial tension load as being 50 kilonewtons in here. And then now that we've done that, the rest of the spreadsheet is just auto calculated for us. So if I go to section 5, it checks all of the bolt spacings, and we can see that in here it's all passing. If for example I put in another bolt row, went up to number 3 bolt rows, you can clearly see this is going to foul, but in the diagram here in section 7, but in section 5 it also tells us we're going to foul. And when we foul on our geometry, it auto crosses out all the rest of this spreadsheet to force us to put in a sensible spacing and a sensible number of bolt rows. So let's go back to 2 bolt rows and continue. In the next section we're looking at the resistance of the gross cross section. So this is looking at the overall cross section of the flat plate. So if I have my flat plate again in here drawn, and we have some bolts like that, when we're looking at the gross cross section, we're looking at this entire area in here. We're looking at that failing, okay, and that's borne out in the equations. So in here we can see that the gross cross sectional area is just the height of our section times the thickness of our section, and then we're looking at the strength of that when we multiply that by the yield strength of our steel. So that's the checks on the gross cross section. Section 9 is looking at the net cross section. So this is looking at the reduced cross section, allowing for the bolt holes. So if I go back to my drawing, it's looking at the section in here. Okay, the section that is reduced because we've got holes due to the bolts. Okay, and that formula is in here. That's our A net formula, and we've got a different safety factor to deal with that. And now again, we work out our design ultimate resistance at the reduced cross section, and then we check that against our applied load. The next bit, we look at the shear between the bolt hole columns. So for example, if I go back to this drawing, let's just do a new drawing again. When I have my flat plate, and let's say we have 2 bolt hole columns, and false over here, we'll have a shear surface between these 2 bolts, like that, a potential failure zone in shear, and the spreadsheet checks that for us, so to make sure we don't have a shear failure through there. And then finally, we check the resistance of the bolts. We work out the resistance of the bolts based on what bolt size we have and the bolt class, and then we check that against our applied loading. And the resistance of the bolts has been taken from the steel building design data, also known as the Blue Book, and that can be accessed online. If you just Google Blue Book online, you'll find all of the data for these bolts from there. So that's basically the spreadsheet. There's also a worked example, PDF worked example, which downloads when you download the spreadsheet, and I recommend having a quick look through that as well, as it gives more detailed information on all of these calculations. I hope that was of use, and I'll catch you in the next one.